So hi everyone, I'm a PhD student from Comenius University in Bratislava. So today my talk is devoted to Josephson junction parametric amplifiers. So actually, what the idea of traveling wave amplifier? Let's say we have a weak signal from our qubit, and we need to somehow amplify it. And the idea is to apply a pump, a signal with a high power to our amplifier, and to perform somehow wave mixing between the pump and signal, and as a result obtain amplified signal. And this wave mixing can be performed by like nonlinear media, and in our case is a series of Josephson junctions. So the point is of making the series of junctions is that at first we want to broadband amplifier, so it means that we need to amplify a big range of frequencies. And the second is that we can prove that as much junction we have, as much gain we will have at the end. So such system can be described by such a Lagrangian. It's simply, we see that here is a Josephson junction, here is a kinetic term that related with ground capacitance, and here is also Josephson junction capacitance. It's written in a phase variable, which can be defined such a way. So the first derivative of phase is voltage, phi0 is flux quantum. So the next, we can write the equation of motion of our system. The first one is coupling with our input. The last one is output, and the middle one is just our amplifier. So solving this system of equation, we can obtain voltage and current, and to calculate by definition S21. And our transmission by definition is have a such formula. So what does it mean? If the transmission is positive, we have a gain. And so what we want to do actually is somehow manipulate parameter of our circuit and make this guy as big as it possible. So fortunately, we forgot to mention it's about like 2,000 or 3,000 equations. Like usually length of amplifier is like 2,000 or 3,000 Josephson junctions. So fortunately, we don't need to solve the system by ourselves, and we can use such programs. VRSpice is old one, and like there are a lot of publication with such program, and Josim is new one, and I haven't seen any publication with that one. But the point is that this one simulate like 2 times faster, and as we see in the next slide, that they give more or less same result. So parametric amplifier work in such a way that it always have a regime where it amplify the best way. So let's say if we put too much power to our system, our current in junction will be very close to critical current, and that will give us like bifurcation regime when we have like 2 solutions in 1 point. And that is why in that regime we will have some crazy stuff which decrease our gain. From other side, if you put lower power, our nonlinearity will not be such big, and amplification will be lower. So in simulation we do the same as an experiment. We just try different powers and put it's not very good so and put different frequencies of power and signal. Here is in the x-axis is a signal, y is pump, and the color bar is the gain. So let's see that in VRSpice we need to lower power to obtain the optimal regime. All fourth picture, like this picture is the best gains that we can obtain in our sample parametric amplifier. And what actually we see that this region where is actually amplification occurs and is the same in both programs. The second, we see this like kind of sabers. It's nothing but just Fabry-Perot resonances, but due to non-linearity, they look like that way. So what now? We have our classical theory, and we know how to solve it. So what can we do with that? We can simulate the impedance, due to impedance is purely classical quantity. So what the point of such impedance? That okay, we can actually make very nice amplifier, and like it will have a big gain and big range. But if it not impedance matched with our input, which is usually 50 ohm, we will have so-called ripples, because like if we have an impedance mismatching, big impedance mismatching, some frequencies will be amplified, but other frequencies will be like suppressed, because like almost all power in some frequencies will be reflected. And so to perform this impedance matching, we use the idea from just electrical engineering to perform the taper. Taper is such a thing that smoothly change impedance from one value to another. And here is the example, the simplest taper that exists is linear taper. So what we offer is to make a taper with Josephson junctions. And how we do this is that we can manipulate the distance, which we can like put the junction in different distance from each other. And that is way to build this impedance function. As you see, it can be seen from this formula. Here is L is inductance, and delta X is distance between two junctions. It's not, it's a capacity density. And so from this, it's obvious that we can do this by changing the distance between junctions. So let's see how it works. This picture is actually a transmission for a small signal. And we see that in the lower frequencies, we have like bad transition, but as frequencies increased, our transmission is like increased too. Like it means that 0 point, it means that almost all power that we put to our device is go to our device. But this point, it means that like a lot of power is reflected. And the taper makes the thing that in such region we have very good transition. So and it works like from this region. So now let's apply a pump to see how it works like in like nonlinear regime, and we see that it like more or less works. We have decreased such impedance match ripples. It's almost about 0.5 dB. So thank you for your attention. Actually, it's a good question. All amplifiers actually amplified in both directions. If let's say you put signal here and pump here, it will amplify signal here. But also, if you put signal here and pump here, it also will amplify the signal. And the point is that when we put like your QBTU amplifier, you have a noise from output because it's connected to the environment, and the noise will be amplified too. And it's a problem which I didn't tell you in my talk, that we want to make amplifier such a way that it's amplified in one direction, but it doesn't amplify in another. But almost all amplifiers have such a disadvantage. Yeah, it's possible actually, but if your impedance match, your reflection is almost 0 in that sense. We want to make it impedance match to decrease such a reflection. But it could be also made in such a way that we make so big impedance mismatch, so in our reflection could help us to obtain the gain. But like it's another idea which our group used, but I didn't tell you here. Yeah.